Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Aizuddin Muhammad. So today I'm going to present you about the module 8, acetic acid and synthesis and application. So this is my team member of my group. Me and myself, Ahmad Aizuddin Muhammad, and next is Abdullah Ahmad bin Abdul Halim, and Muiz bin Zakaria, Muhammad Iqbal bin Yusuf, and the last one is Muhammad Zimam Akid bin Muhammad Anifah. So today I'm going to present you about the history of acetic acid production. So acetic acids is mostly used for the production of vinyl acetate and also acetic anhydride and as a solvent. So the first industrial process for the production of synthetic acetic acids was commercialized in 1916. So here's the radical mechanism for the acetaldehyde oxidation. So for the acetaldehyde process, it's still widely used, but since the development of the Monsanto methanol carbonylation process, it has progressively been losing ground. Direct liquid phase oxidation of naphtha or N-butane was once the preferred route to acetic acid because of the low cost of this hydrocarbon. The mechanism for this reaction is also based on the radical. So in 1968, Monsanto introduced a carbonylation process using a novel, highly active and selective rhodium-based catalyst that could operate at much lower pressure. This was commercialized successfully only 2 years later. For years, this process has been the most attractive route for acetic acid manufacture. So, despite the success of the Monsanto process, the search for the new catalyst has continued. The strategies employed have involved either modification to the rhodium-based system or the replacement of radium by another metal, in particular iridium. So very early on, research at Monsanto found that iridium is active in the carbonylation of methanol, but less active than rhodium. The table shows a comparison of the process condition and yield of the various processes, which are very different. The carbonylation technologies are closely related in the Monsanto and Cativa processes. However, the pressure is much lower than in the now obsolete BASF process, resulting in less severe, lower cost operating condition and higher acetic acid yield.
Okay, Assalamualaikum. My name is Muhammad Iqbal Yusuf. I want to explain about methanol carbonylation reaction. Okay, first I want to explain about a simple definition. Methanol carbonylation is an exothermic reaction and thus is thermodynamically favored by low temperature. Okay, this is a simple graph. The methanol equilibrium conversion against temperature. Okay, they have three different pressure, which mean 1 bar, 30 bar, and 300 bar. Methanol equilibrium conversion to acetic acid feed methanol and carbon monoxide equal to 1 mole over mole. This is figure 3.9.3, the simple of graph. Okay, the graph show effect of temperature and pressure on equilibrium conversion of methanol to acetic acid. Okay, in the reaction condition employed, the methanol equilibrium conversion is almost complete. Indeed, also at atmospheric pressure, the conversion is almost complete at the temperature used. However, in order to stabilize the reaction mixture in the liquid phase and to produce and maintain the active form of the catalyst, the reaction is carried out at the elevated pressure. The catalyst complete is not stable at low carbon monoxide pressure. The catalyst is iodine. Iodine, commonly supplied as hydrogen iodide, which is very corrosive, is an integral part of the catalyst scheme. Fortunately, there is basically no free hydrogen iodide as it readily reacts to form methyl iodide with methanol. This is a reaction. Methanol react with hydrogen iodide, form methyl iodide plus water. The heat form of the isothermic equal to negative 53.1 kilojoule per mole. Okay, I will pass to Zima. Next, thank you.
Hi and Assalamualaikum. My name is Muhammad Zimam Akid. To continue what has Iqbal present about methanol carbonylation reaction, so we first go to the catalytic cycle. Okay, this one is the catalytic cycle. It is started from formation of methyl iodide CH3I through carbonylation. That is methyl iodide plus carbon monoxide and becoming CH3COI, that is acetyl iodide. Then the form acetyl iodide is converted to acetic acid with addition of water, becoming acetic acid plus hydrogen iodide. Okay, the next one is the reaction rate indicates a first order dependency on methyl iodide and rhodium concentrations in the rhodium catalyzed Monsanto process. This is the rhodium catalyzed Monsanto process. RCH3COOH equals to K. The reaction rate is independent of the concentration of the two reactants, that is methanol and carbon monoxide. The result of this zero order dependency is that the rate of output at every conversion stage is the same. It is possible to achieve high conversion even in a continuous tank reactor CSTR of relatively small volume. Okay, I think that's all from me and from us. Thank you.
Methanol carbonylation process. The first industrial process for carbonylation of methanol to produce acetic acid was commercialized in 1960 by BASF. This is the flow scheme of the Monsanto acetic acid process. Methanol carbonylation process. Carbon monoxide and methanol are fed to asparagine CSTR containing the catalyst. Reaction takes place in the liquid phase under relatively mild conditions. Non-condensable byproducts, mainly carbon dioxide and hydrogen, which are formed by the water-gas shift reaction, are vent from the reactor. This vent gas is combined with off gas from the light end column and sent to a scrubber to recover the volatile and toxic methyl iodide. Liquid is removed from the reactor through a pressure reduction valve and enters a flash vessel, resulting in a gas and a liquid phase. The liquid phase, which contains the dissolved catalyst complex, is recycled to the reactor. The gas phase, containing most of the acetic acid product, water, methyl acetate, and methyl iodide, is sent to a distillation train for purification. In the light ends column, methyl acetate, methyl iodide, and part of the water are removed and recycled to the reactor. Wet acetic acid is taken as a side stream from this column and fed to the drying column, where dry acetic acid is removed as bottom product. The overhead of the drying column containing a mixture of acetic acid 35% and water are recycled to the reactor. Thus, a fixed amount of acetic acid and water is continuously circulating through the plant. The dry acetic acid is fed to the product column from which heavy byproducts, mainly propionic acid, are removed as bottoms. The carbon monoxide pressure in the flash vessel is low, which may lead to loss of colligans and precipitation of insoluble rhodium species, for example, RHL3. Therefore, a relatively large amount of water, 10 to 15%, must be retained in the process to keep the rhodium catalyst stable and in solution.
Okay, next I will proceed on the Cativa process. As you can see, the figure shows a typical flow of the iridium-based Cativa process. So the Cativa process is actually a method for production of acetic acid from the by the carbonylation of methanol. So the Cativa and Monsanto process are sufficiently similar that they can use the same chemical plant. So this change reduces the number of drying column necessary, decreases formation of byproducts such as propionic acid, and suppresses the water gas shift reaction. So the reactor is not mechanically stirred. A jet loop reactor is used.
A plug flow reactor is installed after the first reactor for increased carbon monoxide conversion. Because the iridium catalyst system is stable at low carbon monoxide pressures, a much lower water concentration can be used. One less distillation column is required, and the lag ends column and drying columns can be combined into a single column. Propionic acid is produced in much smaller amount than in Monsanto process. So in the development of the carbonylation process, corrosion by hydrogen iodide has always been a point of concern. So the key to the success of the Monsanto and Cativa processes is their very active catalyst system, which allows the operation at much less severe conditions than those in the BASF process. Alright. Still, the need for expensive corrosion-resistant construction materials like titanium or even more exotic materials remain. So the titanium is the most often used.